So today we're going to be looking at some acid-base equilibrium review for chemistry 30. Basically what we're going to be looking at today are a bunch of different questions that you can expect to see on your unit exam coming up for this. Let's get started. So first of all, we're going to do some practice on various concepts from the unit today. We're going to look at Le Chat's rule. We're going to look at ice tables. We'll look at the approximation rule for small k values. That's where you're able to keep your initial concentration the same as your equilibrium concentration for your reactant. We're also going to look at some pH and pOH questions. How I want today to work is you'll be given a handout with all these questions on it. I don't want you to run through the handout all together at first. I want us just to work on one question at a time. So in the video, I'll post a question. I'll tell you to pause. I want you to work on it for however long it takes, a couple minutes or whatever. And then we'll unpause and we'll go over it together. This video will be posted on our Google Classroom page in case you wanted to watch it over again. But again, these questions we're going to look at today are very similar to the ones you can expect to see on a unit exam. So there won't be much surprise as long as we study this. Here we go. So first question right out the bat. There are three parts of this one. We're looking at how each of these changes would affect the products or reactants in the equilibrium. So just focus on either products or reactants changing. There's the equilibrium reaction. There's the three questions. Pause the video here. Give it a try. So I'm going to go over this right now. First of all, for number 1A, increase in iodine gas. This is a classic Le Chat's rule question. Basically, we're just talking about how one piece of this changes and how that'll affect the whole system. If we're increasing the iodine gas, which is right here on the right side of the equation, it's like making the right side of the equation heavier. So if you imagine this using our analogy with like a balanced scale, this is how the scale is looking right now. The right side is looking pretty heavy. In order to fix this, equilibrium needs to shift to the left to bring it back to a balance. So since we're shifting left, you could even write that, shift left, what's going to happen in terms of our products and reactants is our reactants are going to have to go up, right? So if we are increasing our iodine gas, in order to compensate, the shift is going to be to the left. We're going to be making more of our reactants. The reactants are going up. Next part, this is, I think, the trickiest of the bunch here. It says, what happens if we increase the temperature? Notice how I give you the enthalpy change, and it's positive 90 kilojoules per mole. If that's our enthalpy change in this reaction, the positive just means the reaction is gaining energy. That means it's absorbing it from somewhere. It's always nicer when we have the energy actually built into the equation itself, but since this is gaining energy, we can see the energy is actually going to be on that left side over here. So if we're increasing the temperature, temperature acts just like any other entity in the reaction. If we're increasing temperature, if we're making it warmer, it's almost like this energy is getting heavier in a way, if we're going to use that analogy. That's going to make the scale tip this way, right? So if it's tipping this way, in order for us to get it back to balanced, we have to make it shift to the right. Because right now it's a little too heavy on the left, we need to shift to the right. If we're shifting to the right, in terms of what that's going to mean for our products or reactants, well, it's going to mean our products are going to have to go up. So the amount of products that we produce is going to increase if we increase the temperature of this. Last one, decrease in volume. This is kind of the odd one out. Whenever we talk about volume or pressure, I always want you to think about it in terms of volume. So if we increased pressure, that'd be the same thing as saying decreasing volume. The reason I say focusing on volume is the way it goes is you look at whatever side has less stuff. If you're decreasing volume, you're going to go to the side with less stuff. If I was increasing volume, you're going to go to the side with more stuff. So when we talk about the amount of stuff, we just have to look at the coefficients, but only of our gases. This guy's a solid, so I'm going to ignore it altogether. On the left side, we have 5 things. On the right side, we have 5 plus 1, so 6 things. Since I'm decreasing volume, I'm going to go to the side with less stuff. That means I'm going to shift to the left, because the left only has 5 things. And again, in terms of products and reactants, I guess if we're shifting to the left, that means my reactants are going to be going up. We're going to be making more reactants if we decrease the volume here. Anyway, next question. I'm not going to read this one to you. I'm sure you can read it on your own. Pause the video here. Give it a try. All right, I'm going to go over this one now. We're looking for the value of Kc for this thing. In order to have a Kc value, we need to know all of our equilibrium concentrations. In order to find those equilibrium concentrations, let's use an ice table because we know some of the initial stuff here. Before I get an ice table though, it's always nice to know what my equilibrium reaction is. We're talking about hydrogen iodide gas decomposing into hydrogen gas and iodine gas. Hydrogen iodide is just HI. This will be an equilibrium reaction, so a double-sided arrow. Hydrogen gas is H2, plus iodine gas is also part of Hofbrinkel, so it'll be I2. Hofbrinkel, of course, are all the elements that exist as more than one. Now, the other thing we got to watch for here is that our equation is balanced. I see there's one H here and two H's here, so I have to put a 2 in front of this, and that actually fixes our I's as well. So now we're all good. Anyway, since we're talking about initial and final concentrations, like I mentioned a minute ago, we have to have an ice table. So if we build the ice table over here, sorry if it's a little shaky, it's hard to do this with a pen tablet. ICE, the ice table is on this side, and then we have our reactants and products. So that would be our 2 HIs. You don't need to put the 2 there if you don't want to, but I like to. It's a good habit to get into. And then we have our H2, and we have our I2. And let's separate this chart into its pieces. There we go. Okay, so what we know at first is that we have 2 moles of HI placed in a 1 liter container. Just a reminder with your ice table, every single number that goes into an ice table must be a concentration in moles per liter. This one's pretty nice. If we have 2 moles per 1 liter, well then that clearly just means we have 2 moles per liter. As for our H2 and I2, the initial condition of those things, we can assume, because it doesn't say we started with any, must be 0. The next row, the change row, is my personal favorite one. We need to use our coefficients in our equilibrium reaction to tell us how many x's we're adding or subtracting. We're subtracting x's away from reactants. So since there are 2 HIs and that's a reactant, we have to go minus 2x. And then for each of these, there's one of each of them, so we have to say plus 1x because they are products, so it'll be plus. Now, equilibrium can often be a bit of a tricky one, but if we scan this question again, we know our final concentration of H2 is this 0.214. That fills it in perfectly right there. And it's always great when we have a vertical column finished, because that means I can now solve for x. Solving for x here is really nice because 0 plus 1x equals this number. So that just tells us that this number is what x is equal to. So we know x is 0.214. That means I know in this column I also have 0.214 because 0 plus x is going to be that. As for this one, 2 minus 2x. So I have to go 2 minus 2 times the x value, which we found was 0.214. Long story short, we're going to get 1.572 as our equilibrium concentration for those 2 HIs. Now, the question is looking for Kc. Kc is just equal to your products over reactants. There's something we haven't seen in a little while that's going to happen in this one that might have caught you, but I'll show you. Kc is going to equal our products, which will be H2 times I2 divided by our reactants. And the only reactant we have is HI. But notice how there's 2 HIs. When we have a coefficient in front of one of these things, that actually becomes an exponent here. The logic behind that is on this H2 plus H2 plus I2, we multiply those together because there were 2 distinct things. 2HI, you could also, in theory, I don't know why you'd actually write it this way, but you could write it as HI plus another HI. So by the same logic, it would have to be HI times HI on the bottom there. That's why we just square it. If that was like a 3 or a 4 in front of it, then it'd be cubed or to the power of 4 as well. It all works the same. Anyway, to find the Kc value, we need to use only our equilibrium numbers here. So let's throw those in here. We know H2 is 0.214. We know I2 is also 0.214. And we know HI is 1.572, but we have to square that number. Throw that in your calculator into 3 sig digs, because that's what it is in this question. We didn't use the 35 degrees, so it's not 2 sig digs. It's 3 sig digs in this question. It's going to be 0.0185. Or I guess you could say 1.85 times 10 to the negative 2. Whatever floats your boat. And remember, there's no units on Kc. It's just the number. All right, next question here. So calculate the concentration of gases produced when 0.1 mole per liter of CoCl2 decomposes into carbon dioxide and chlorine gas. And I give you the Kc for the reaction right there. Pause the video here, give it a shot. All right, so I'm going to go over this one now. I'm going to start with a balanced equation, just like we did in the last one. This one's going to work really nice, actually. COCl2, it told us it's decomposing. We'll do a double-sided equilibrium reaction on this just because, but it's decomposing into carbon monoxide and chlorine gas. Carbon monoxide is just CO. Chlorine gas is Cl2. So look at that. It's like COCl2. We don't even need any numbers in front of this thing. This thing actually broke down really well. Let's now make an ice table for this because we know this was our initial amount of COCl2. Let's see if we can dig out the other stuff here. So if I build myself an ice table, I'll put my COCl2 here, and then CO and Cl2, and then finish up the ice. Box it all in. I guess I could save time by not boxing it in, but I think it just looks more organized if I do that. Anyway, so we know 0.100 moles per liter is what we had of the COCl2, so I'll put that number right there. We can safely assume we didn't have any CO or Cl2 to begin with because it doesn't say we did. It's decomposing into it, so we can assume we started with none. Now we got to use our coefficients to put the whole x thing in here because this is a reactant. It's going to be minus 1x. These are products, so it's got to be plus 1x. And then this is where we hit a bit of a wall, right? So on the last question we had, at least I gave you one of the equilibrium conditions. But in this one, I didn't give you any equilibrium stuff. The only thing I gave you was that Kc of the reaction. But I want you to notice the Kc of this reaction is a really tiny number. It's 10 to the negative 10. That's really, really, really tiny. Well, there's a rule that says if the difference between these two things, oops, sorry, my screen just went weird here. Let's see if I fix that. I think it just paused here. Let's see if I can fix that. Unpause this here. Is it going to let me? Is it going to let me? It doesn't look like it's going to let me. Uh-oh. Uh-oh. Is it not going to let me here? Share that again. I think we're back in business now. Sorry about that, guys. There was like a really weird glitch that just happened there. Hopefully you can see the screen again. Looks like we can. Anyway, sorry about that. So anyway, the issue I was trying to get at here is we have a really small Kc value. The rule is that if the Kc value and the initial concentration are 1,000 times apart or more, you can use something called an approximation rule. The approximation rule just says you can take your initial concentration and say it's equal to your final equilibrium concentration, which is exactly what we're going to do here. So 0.100 is going to be my final equilibrium concentration, and I can do that because my Kc value is tiny. The logic behind that tiny Kc value is Kc just tells you how much your reaction goes to completion. If you have a really small Kc value, your reaction is not going to be completing very much. It's going to be really stalled. It's not going to really happen too much. Because it's not happening very much, you're not going to see any noticeable change in your reactant because the reaction is not going very far. That begs the question though. If the reaction is not going very far, mathematically it almost looks like x is just equal to 0 here. We can't assume that though. X is actually just going to be a really tiny number. So let's play with these numbers a little bit. We can say 0 plus 1x is going to be x for this column, and same with this one, 0 plus 1x is x for this column. Now let's use our Kc equation to see if we can solve for x. We know the Kc value is 2.2 times 10 to the negative 10. This is going to equal our products, which is x times x, so x squared, over our reactant, which is 0.100. Clearly now we can solve for x. We just need to multiply that 0.100 over and then square root it. Long story short, if I do that, I'm going to get x equals to 2 sig digs here, 4.7 times 10 to the negative 6, and that would be moles per liter because these are all measured in moles per liter. That's actually what the question was asking. It was looking for the concentration of gases produced. Those are both gases, CO and Cl2. That's the concentration of those gases being produced. So honestly, a little bit of a shorter question than the last one, but the trick was we had to look at that very small Kc value and understand we had to use the approximation rule that said we could just keep the final concentration the same as the initial one. Anyway, hopefully I explained that well. Let's move on to question 4. This is technically the second last question. The last one has 3 parts to it, but we'll get there when we get there. Anyway, the pH of a 0.400 mole per liter solution of sulfurous acid is measured to be 1.17. Calculate the Ka for sulfurous acid from this evidence. Pause the video here, give it a try. All right, I'm going to go over this one now as well. Just like before, let's start with a balanced equilibrium reaction. Sulfurous acid, if you don't remember what that is, I wouldn't blame you. Oops, I just went forward there. If you didn't remember what sulfurous acid was, I wouldn't blame you. You could just look in your data booklet to find it. It's actually H2SO3. Now, the reaction we're going to have here, because it doesn't say we're mixing it with anything else, we can assume it's an ionization reaction. That's how we dig out a Ka value to begin with. Ka and Kb are found by ionizing your acid or your base. Ionizing it just means mixing it with water. So if we mix H2SO3 with water, this is going to become an acid ionization reaction, which according to Bronsted-Lowry would mean that we have to lose an H from this H2SO3, which would drop it down to HSO3 negative. And then that H is going to be transferred onto H2O to become H3O positive. That's hydronium. That's a key piece of evidence that we have an acid that just ionized because it was able to produce that. Now, we want to find that Ka value. Ka, of course, comes from our equilibrium amounts. Let's set up an ice table just to see what we got going on. Ice tables are a really good way of seeing what sort of things are happening both before and after equilibrium, right? So ice, and then let's set up our things. We're not going to include water in this because water is technically a liquid and these other ones are all aqueous. We want to keep our states all the same. So H2SO3, and then HSO3 negative and H3O positive. All right, so if I fill out the rest of this table here, let's get all those boxes going. The only thing we know to start with is that we had 0.400 moles per liter of sulfurous acid. So 0.400. We can assume these were both 0. We can use our coefficients just like in the other ones to make our C row. I always like this row because it's pretty predictable. So this will be minus 1x, this will be plus 1x, and this will be plus 1x. But then once again, we hit a bit of a wall. The last example, we were able to fill out some of our equilibrium stuff because we had a really small Kc value. Now, you could, to be honest, this might be at the back of your mind right now, you might say, well, we could look in our data table and find the Ka value for sulfurous acid. It's already in there. Why on earth would we be going to all this work to solve for it when if you just looked in your data booklet, you could see it? We can't do that because in this case, I have a measured pH from a known concentration solution. So it's almost like we're looking for an experimental Ka value for this. So we can't just use our formula sheet to make that jump this time. Instead, what we got to try to do is we got to try to use that pH. I'm just going to remind you, there's a formula that connects pH to your H3O concentration. And that formula is H3O plus, that's your concentration, equals 10 to the negative pH. This is one of those formulas you just have to memorize. 10 to the negative pH to me has a nice ring to it. You know, like you go 10 to the negative pH. That's got to be something, right? It's not 10 to the negative H3O positive. That doesn't sound like something we've been using before. It's 10 to the negative pH. So you just got to really drive that in. Anyway, we know the pH is 1.17. So we can say this is 10 to the negative 1.17. Throw that in your calculator and you're going to find that that number is going to be 0.067608. That is our concentration of H3O plus. So I can fill that in right here. 0.067608. That's my equilibrium concentration of H3O plus. Notice the rest of this. That would mean this would be our X term. So from this column right here, because it matches the H3O one, I know this number is also going to be 0.067608. And then as for this final column here, 0.400 minus 1x, well, we know x is just this number because 0 plus x is this, so this number must be x. We can just subtract that number from 0.400. And the answer you get for that is 0.33239. And again, I'm just keeping however many decimals I'm comfortable with. That's just how far I went. You might have gone farther, you might have gone not as far. It is what it is. The more decimals you keep, the more accurate the results will be. So it is what it is, right? Anyway, we now have enough information to solve for Ka. Ka is just your products over your reactants at equilibrium. Let's roll on this one. So Ka, just box this away just so we don't get confused. Ka is going to equal our products. That's both these numbers here. I'm going to be lazy. I'm going to say 0.067608. Since there's two of them, I could write the number again, but I'll be lazy and I'll just say squared because multiplying it by itself is the same thing as squaring it. Whatever, is what it is. Anyway, and then this one, that'd be 0.33, sorry, that was a bad 3 there, 33239. Anyway, throw that in your calculator, and we want, it looks like just 2 sig digs in this question. The reason it's 2 and not 3 sig digs is remember pH, it's only the decimals count for sig digs, so there's just 2 sig digs on that. I'm getting 0.014, or I guess you could say 1.4 times 10 to the negative 2. All right, home stretch here. This is going a little longer than I thought it would, but that's okay. That's okay. We can take our time on these sort of things. So I've decided to put 5A and 5B on one slide. I want you guys to try these questions first before we move on to 5C. I'll show you the answer to this. It'll really set you up. It'll help you with 5C. Pause the video here and unpause when you're ready. All right, so I'm going to go over this one now. 5A, that's that first one there, just talking about CN acting as a base in ionization. This is a super quick one. We just want the balanced Bronsted-Lowry equation. That just means since this is acting as a base, we know from Bronsted-Lowry that it's going to be gaining an H. So we've got CN negative. Of course, it's ionizing, so we have to say plus H2O. But it's going to be gaining an H because it's acting as a base. So this is going to become HCN. Plus, the H it came from was one of these ones, so it's going to drop an H from the H2O. That's just going to leave us with OH negative. That's all you got to put on that one. That's like literally as far as you need to go. Oh, I just realized. Oh, never mind. I was going to say there's got to be a charge here, but no, there doesn't. We're all good. We're all good. I was almost going to put a plus there. Anyway, that's all we had to do on that one. We just had to make the Bronsted-Lowry equation for that. We're all good. Let's move on to part B of this. Calculate the Kb value for Cn negative. It actually wants us to calculate one. From this ionization reaction that we have here, we could have said the Kb value was just this concentration of HCN times by this concentration of OH divided by this concentration of CN negative. But we don't know any of those concentrations here. We don't know any of that stuff, right? Since we don't know any of those concentrations, we need to take a look at our data booklet and see if we can find something we can use as a Ka value. Your data booklet, of course, on your acid chart doesn't have Kb values. It has Ka values. But here's the trick. We're interested in finding the Kb value for Cn negative. See if you can find Cn negative on your data booklet in that second from the right column, the one that's titled conjugate base formula, because this guy is really the conjugate base to this guy. This is, if we wrote it this way, this is the base and this is the conjugate acid, but it flips around as well. We could say this is the acid and this is the conjugate base, right? If you take a look at your data booklet, you're going to actually see that for HCN and CN, there's a Ka value on your data booklet of 6.2 times 10 to the negative 10. So again, I'm pulling that right out of the data booklet. We don't want the Ka value for this. We want the Kb for its conjugate base. Well, between conjugate acids and bases, there's a really special relationship that exists. It's Kw equals Ka times Kb. Kw is just 1.0 times 10 to the negative 14. That's another one of the things in this course you just have to remember. So we can just say that that's equal to that 6.2 times 10 to the negative 10 times Kb. To solve for Kb, we just need to divide this whole chunk over. And I would divide it in brackets and everything. So I put brackets on this guy, divide by brackets around that 6.2 times 10 to the negative 10. You're going to get Kb equals, to just 2 sig digs here, 1.6 times 10 to the negative 5. And you'll really want to keep that number safe. The reason being is we need it for part C. So question 5C, this is the last question of the day, thank goodness. Calculate the pH and pOH if the initial concentration of Cn negative is 0.75 mole per liter. Before you pause the video here, here's a massive hint. It's an initial concentration. What kind of thing are we going to do to set this up? Pause the video here, give it a try. So to go over this one, since I was given an initial concentration, this hopefully tells us that we need to use an ice table. So for the last time today, we'll set up yet another ice table. My formula was on the other slide, but I remember it's going to be Cn negative, HCN, and OH negative. box these things up just so we can keep them all organized here. All right, so we know the initial concentration of Cn negative is 0.75. We can make a safe assumption that these guys are zero because they are our products. For the change column, you use the coefficients. Again, that comes from the last slide. That would be minus 1x, plus 1x, and plus 1x. And usually here, this is where we'd hit a bit of a wall once again. But remember, one of the last things I told you on the last slide was that Kb value was going to be important. Kb is 1.6 times 10 to the negative 5. Notice how small that number is, 10 to the negative 5. That is more than 1,000 times smaller than that 0.75 there. Because it's more than 1,000 times smaller, we can use the approximation rule. That's where you keep the initial number and the final number the same. Now again, to the untrained eye, it looks like x might equal 0 here. We can never make the assumption that x is just going to be 0. That's not how these work. Let's solve for x, because 0 plus 1x is x, and 0 plus 1x is another x. Let's solve for x using our Kb formula. And we have to use the Kb one because the original part of the ionization was our base. We can't use the Ka number here because Cn negative is a base, or at least acting as a base in this question. So Kb value is 1.6 times 10 to the negative 5. That's going to equal your products, so x times x would be x squared, over your reactant, which is 0.75. Once again, solve for x. Let's multiply 0.75 over and then square root. X is going to equal 0.0034641. That's the concentration of each of these things, including your OH. We now know the concentration of OH. We're trying to find pH and POH. POH links directly to OH. There's a formula to calculate POH. It's a bit different than the one we saw earlier today in terms of like 10 to the negative pH, right? It's not quite that one. The POH formula, which is another formula you guys have to just remember, is POH equals negative log of your OH concentration. Our OH concentration we just found was this number here. So let's throw that in. POH equals negative log of 0.0034641. This gives me a POH to just 2 sig digs here of 2.46. And again, that is 2 sig digs because with pH and POH, it's only the numbers after the decimal that count. So there's your POH. We also want the pH. pH is pretty easy to find once you find POH. It's just the 14 rule. That means 14 minus your POH, so 14 minus 2.46. That will give us a pH, finally, to end the day up, of 11.54. Woo! Okay, so that was a lot longer than I expected. I bet that actually might take longer than one class, and if it did, well, thank you for, sticking through it. But for practice, really, really, really important, that first thing there. Read through your printed notes from this unit. If you've been reading through your printed notes from this unit, you may have noticed that question 1, 2, 3, and 4, I literally just pulled out of your notes booklet today. So, mwaha! All of that was a scam. I already did those questions with you before. That's how familiar it seemed. Question 5, though, A, B, and C, I just made that one up. That was brand new. But still, those first 4, I just took them right from your printed notes booklet. Still, though, read through that whole booklet. It's a very, very, very useful resource. You need to be reading through it to make sure you're understanding all the concepts that we've covered in here, especially some of those old little definitions. For other practice, the 2019 diploma is great practice. The questions from number 30 onwards are about this unit. Some of the questions tie in some other stuff, like there's a 1 or 2 in there that ties in organic chem. If you don't want to touch those for now, you don't have to. I'm not going to be hitting organic chemistry stuff on this unit exam, but our diploma is only a couple weeks away, so it wouldn't hurt to review those things as well. Another handout I have for you is the Chemistry 30 Acid and Base Equilibrium Unit Review handout. It is massive. There's so many questions in it. Pick and choose your battles here, but the answers are on the back page of that one. And just for your information, the unit exam will contain 10 multiple choice, 4 numeric response, and 2 written response questions. Unlike other unit exams, this one is only in 1 part. As always, if you have any questions or if you need any help, please reach out, send me an email. I'm more than happy to help you out. Best of luck.